Okay, so welcome to our second tutorial of the day, which is again alternatives to explicit state space search, and this time we're talking about decoupled search. So just a very quick note, where before Álvaro told you that BDDs or symbolic search in general captures structure of the problem implicitly. So either you're lucky and the BDD gets it, or you're not. In decoupled search, we explicitly need to do that. We need to tell the search how to decompose the problem in order to gain something. So again, for those of you that don't know us yet, I'm Daniel, there's Álvaro. We're working in the Saarland University, and the target audience is, as in our previous tutorial, basically you should be familiar with FDR or SAS+, however you like to call it, planning as heuristic search and the state space explosion problem, and again, ask questions if you don't understand something. The agenda of this tutorial will be quite similar to that of the last one. So we give a brief introduction to planning. I will explain to you the intuition of decoupled search, like what does this decoupling do. We will go into the details of the search, how does it perform, when does it perform good, when not, how to do all the details. Then, like in symbolic search, we can also apply heuristics, actually a bit easier than when you use BDDs. I will explain to you what duplicate checking is. Actually, Álvaro will do these two chapters. So we don't do duplicate checking, that's the answer. Then the big question, how to decompose the task, so factoring strategies. And in the end, we will go into the implementation. And I've prepared a very small hands-on where you can, if you want to implement your own heuristic function. If you want to do that, then just prepare your laptops when we are approaching the implementation section. And I will point out some open topics, like what can still be done, how to extend decoupled search. So yeah, classical planning, as before, we have our classical planning task. We have state variables and actions that change the states. We want to achieve a certain goal condition by applying actions from the initial state. The running example will be as in our previous example. We have the truck and 4 packages that need to be transported on the map. The semantics of the planning task, I will go a bit more into detail about this time because I used the notation quite a bit. So we have the set of all states, which is all different complete assignments to the variables. The labels, like to get from one state to the other, the label would be an action, and the transition is induced by such an action. We have a transition from state S to S prime whenever the precondition of the action is subset of the state, so the precondition is fulfilled, and the successor state arises from applying the action A in these double brackets to the state S. So we say that the action is applicable if the precondition is a subset of a state. By applying the action, we change the value of all effect variables V here to their effect value. And the successor operation is not defined if the action is not applicable. We want to get from our initial state to the goal states, plans, so sequences of actions will get you there, will get us there, and an optimal plan has minimum summed up action cost. One of the most successful approaches, heuristic search. I'm not going to bother you with this a lot longer. So you expand the initial state, you keep expanding and estimate the distance to the goal. A difference to the talk before, again, the alternatives to state space search are the same. We have planning as start property, directed reachability, and one interesting relation here is between decoupled search and Petri net unfolding, because you can see decoupled search as a type of Petri net unfolding where you fix the factors. We will go into details later, and the costly operation of determining the extensions of the unfolding, which is NP-complete for the Petri net unfolding, is a lot easier to do in decoupled search. But there's certainly some relation. We don't have any formal proofs about this yet. We're working on it. Another interesting relation is between decoupled search and factored planning. In fact, decoupled search is a form of factored planning where you decompose your planning problem. So you decompose it into several subproblems, where each subproblem only considers a subset of the variables. You solve the problems, the subproblems individually, and try to combine them somehow again to get an overall solution. Again, details later. So if we are faced with a planning problem, we have the classical state space explosion issue. Due to huge branching factors or other issues, the state space or the search space of a planning problem is exponential, and to find a solution is really a hard problem. Although heuristic search can do quite well, there are some aspects that it just cannot exploit, and this is where decoupling comes into play. One more remark about this is basically a result from Malte and Gabi, who proved that even with a close to perfect heuristic, your search space can still be exponential. So what is decoupled search? What's the idea behind this? What you see here is the causal graph of our running example, which captures the dependencies between the state variables. So these dependencies arise from the precondition and effects of the actions. So from the action descriptions, I will go into the details about this later. So what's important is that you have these dependencies, and what you see here nicely is already like a nice star structure. You have the truck in the center and the packages as leaves around. And what you also see is that given an instantiation of the truck, the packages are conditionally independent. And this is really the key thing that we are going to exploit in decoupled search, this conditional independence of the packages or of the leaf in general. How do we do this? Well, we only branch over center actions, so actions affecting the center in the search, and enumerate all possible movements of the packages or in general of the leaves. So in our running example, again, the center actions would be drives. So the only thing we do is we apply drive actions. So we drive the truck from L1 to L2 and back, or further on to L3 and so on. And we keep track of all possible load-unload action sequences that we can do given such a sequence of drive actions. Let me show this to you given with an example. So given such a center path, where we drive the truck from L1 to L2 to L3 and back to L1. A possible leaf movement, a possible load-unload sequence of a package would be to unload it in L1, then drive the truck, and then unload the package here and continue with the drives. Alternatively, you could choose to load it, drive twice to L3, and only then unload the package. The same works for a package that starts in L3. We could decide to load it once the truck is here, and unload it in the middle or in the leftmost position. And now the important thing is that no matter which of the paths we choose for say the blue package, we are still free to choose any path or even no path for the red package. And this is because the packages are conditionally independent. So this allows us to maintain all compliant paths, which means all paths that can be embedded into the center action sequence for each of the leaves separately. So we really enumerate all these paths. Now you might wonder, well, how does that help me? And the answer is basically here in the table, where you see data where we explore the entire state space of a planning task. We compare standard search, so just explicit forward search, partial order reduction, so standard forward search plus partial order reduction, also Petri net unfolding. There have been tools developed that can do Petri net unfolding for planning tasks, and decoupled search. In the left part here you see how many state spaces could be completely built using each of the approaches, and what you clearly see is that for decoupled search it really works just very well. We can really compress the state space by a huge amount, and thereby build the entire state spaces of many planning tasks. On the right hand side you see what we call the representation size, which roughly corresponds to the amount of data that you need to keep in memory to represent the entire state space. And again, what you see is that decoupled search against partial order reduction and standard search is able to really compress the state space by huge amounts. Look at TPP, where the representation is 6 orders of magnitude smaller than for the explicit search, and also for search under partial order reduction. Anyone familiar with Petri net unfolding? No? Well, then I can probably just skip that. So in Petri net unfolding, it's hard to compute the reachable markings. As I said, that's an NP-complete problem. And decoupled search is able to solve this by fixing kind of the factoring. So if you would do something similar for Petri net unfolding, the behavior would also be similar. So they would be exploiting similar features of your planning task. So let's go into all the nice details. First, I want to define what a factoring actually is. So a factoring F, we say factoring F is a partitioning of your state variables into non-empty subsets. So you take all your variables, you partition them in some way, and this is a factoring. What's more interesting to us is what is a star factoring. We call a factoring a star factoring if it has more than one factor. Otherwise, it would be just an explicit representation. And there exists an FC, so a center factor, such that all actions either affect the center, so have an effect on a variable that is in the center component, or all their effects are within a single leaf factor, and the preconditions of all of leaf actions can be on the leaf plus the center. So again, the center actions can interact arbitrarily with the entire task. An action that does not affect the center really only is allowed to only affect a single other factor, which is a leaf, and have preconditions additionally on the center. Some notation conventions. So basically, a factoring F is composed of a center factor, FC, and a set of leaves, FL. Center actions are those actions that have an effect on a variable in FC. Leaf actions have an effect only on one leaf. Center states are complete assignments to the center factor, and leaf states are complete assignments to one of the leaf factors. Note that they don't have to be of equal size. So we can have leaves, a leaf that only contains a single variable, and others that contain multiple variables. That doesn't matter. So what is a decoupled state? Basically, a decoupled state consists, or is a triple that consists of the center path that leads to this state. So in our case, a sequence of drive actions. This results in a unique center state, of course. And the more important thing is the pricing function. So what I've shown you before, like these compliant paths, these load-unload action sequences, will get translated into what we call the pricing functions. Details about this in a couple of slides, which capture all possible compliant paths, basically, all cheapest compliant paths. Yeah, so the pricing function basically assigns each leaf state a non-negative value. So either a finite number or infinity if this leaf state is not reachable given the current center path. Here's an example of a decoupled state on the right-hand side. So on the left, that's like just a graphical representation of the initial state of our task. And on the right, you see the decoupled state that represents this and actually a bit more. So what we have in the center is our center state. So the truck is in L1. It's in the center. That's like a unique assignment. And all around, you have these table-like data structures that store the pricing function given one leaf. So, for example, in the upper left corner, you have the pricing function for package 1. What does that mean? Well, we can have the package in location 1, because it's starting here, at a cost of 0. So it's in the initial state. We don't have to do anything to get the package into this position. We could also choose to load the package now already, because the truck is in L1, and one possible movement of package 1 is to just load it into the truck. Assuming unit action cost, this gives us a price of 1. We cannot have the package in location 2 or 3 just because the truck didn't do any drive yet. So, I mean, without any truck movement, we cannot get the package to this position. So it's just the same for package 2, and for packages 3 and 4, we cannot do anything, well, just because the truck is not there. So there's no possible leave action that we can apply. So I've been talking to you about compliant paths already, and we capture the set of all compliant paths by a structure we call the compliant path graph. So what you've seen in our example here, only for one package, is given a sequence of center actions, we enumerate all possible movements of the leaves. So what you have seen here is like two possibilities, but there could be a lot more. And this is captured by the compliant path graph. Now this looks really ugly. It's not as bad as it looks like. So let's just go through this slowly. The compliant path graph basically is a layered graph where you start at the initial state, and by applying a new center action, you also generate a new layer. So for each center action you apply, you get a new layer, which is basically a copy of all possible leaf states, and now there are transitions between those states that represent all the compliant paths. This subscript T here is basically to indicate, so for every leaf state we have a subscript T that says in which state, so in which layer this leaf state is. So basically in every layer we have a copy of every possible leaf state. And now if we are in layer 1, this means we did not apply any center action yet. In layer 2 we applied 2 center actions. So there's 2 types of transitions in this compliant path graphs. And the first one is leaf actions that are within a layer. They do not go from one layer to the other. It's really just in the layer, and we have a transition from a state S to a state S prime if and only if S and S prime are really leaf states of this current leaf factor, and AL is also a leaf action of this leaf factor. This expression here says that the center precondition of the leaf action must be true, which in our example means we cannot load a package that is in position 2 if the truck is at a different position. So the center action must be fulfilled. This part is saying that also SL, so the state that we start from, needs to obviously fulfill the leaf precondition of our action AL. And applying AL to SL gives us SL prime. Now to get from one layer to the next, we have these zero cost transitions where, as you see, the index is increased. So really the time steps one step further. This is like labeled by a center action. We don't actually add the center action here. We just say it has cost of 1 because the cost for this is catered for in the search. Like if we branch over actions, we cater for this cost in the center search, and we don't have to do that within the leaves. So again, we have a transition from one layer to the next. If we are talking about 2 leaf states from the same leaf factor, then only if the leaf states fulfill the leaf precondition of a center action, and possible leaf effects changed one leaf state to the other. So in our example, this does not happen because we have a nice fork factoring where center actions only change the center and they don't change the leaf. Now you could also imagine having center actions that while driving from A to B automatically unload all packages that are loaded at position B. And in this case, obviously only packages that are loaded can be unloaded after the drive. And their leaf state of being in the truck is not valid anymore because, I mean, the center action forces the leaves to be, the packages to be unloaded at the destination. So this really changes. So applying a center action can change the leaf states. After this nasty definition, let's go into some example. So basically this is the running example that I told you before. And this is like one layer in our search. We did not apply any center action yet. The truck is in L1, and one thing we can do with the leaf from the initial state that is underlined here, we can load the package into the truck. Or we can also decide to unload it again, but that doesn't make any sense because we have the package at this position already, so the cheapest path is just do nothing. If we apply a center action, say we drive from L1 to L2, this gives us new possibilities in the leaves. So basically these are like these zero cost transitions that I told you. All leaf states that we have in the first layer are compliant with the center action. So this action here does not have any leaf precondition. So we can just decide not to do anything and keep the package in location L1, for example. Now the new possibility that we have is once the truck has driven to L2, we can choose to unload the package to this position, which gives us a new possibility, a new leaf action sequence, a new compliant path. Now a question, what would be the price of this state? Anyone want to guess? So it's really just following from the initial state all transitions that lead to this state. 1. Next try. Yeah, 2. So the point is, from the initial state, what we need to do is we load the package. This transition here comes for free because it's done by the center, and then we unload here, which sums up to a price of 2. Yeah? Okay, so let's do another center action. We drive further on from L2 to L3, and now what happens, again, because this center action does not have any leaf precondition, all these leaf states are still available. So still, after the truck has moved to L3, we could choose to do just nothing with our package and leave it in the initial state, because the truck does not depend in any way on the package. And in this case now we could choose if we loaded it here, so basically if we decided to load the package, then we wait until the 2 tries are over, and then we can choose to unload the package to location L3, again at a total cost of 2. So 1 load, drive, and unload, when we only count the cost of leaf actions. Yeah, we can continue. I guess by now you have understood the principle. So we apply another center action, and now the only difference is that in this layer here, so really this here is one decoupled state, there's nothing new that we can achieve, and there's nothing that we have achieved already that we could possibly achieve by a cheaper price. So we only keep the cheapest compliant paths. We could also obviously unload and load the package in location 2 and then unload it again in location L3, but it's not the cheapest path. It contains cycles, so we just skip those. Okay, so let's do another example that's a bit more complicated, because now the truck actually has a leaf precondition. To be a bit more specific, whenever we drive the truck from location X to location Y, we require that one package, an arbitrary one, so package Z, is loaded in the truck. So basically here. The truck needs to be at location X like usual, and some package needs to be loaded. For the initial state, that doesn't change anything, because, well, without a drive, we can still load the package into the truck or keep it in the initial at its initial location. Now, if we drive the truck from location 1 to 2, together with having package 1 loaded, so this is really a requirement for the center action, then we cannot, we don't have a transition from location 1 to location 1 here anymore with the cost of 0, because this is no longer compliant. Right? So to be able to perform this drive action, we need that the package to be loaded in the truck. Otherwise, we could not do this drive action, and that's why location L1 is no longer available for the package. Once we've driven to L2, we can again choose to unload the package at a cost of 1, giving us the same pricing function, the same price for this leaf state. Say now we drive on and again use package 1, then basically the same happens. We cannot, so the location 2 is no longer compliant with this decoupled state here, because we require the package to be in the truck. Like with this precondition up here, once we apply the center action, we can no longer choose the package here to be in location 1. That's no longer compliant. Say in the last center transition center action that we apply, we do not require package 1 but package 2 to be loaded. Then basically it's as before again, we can decide to either keep the package in the truck or to have it unloaded at location L3, although the truck has driven back, because the truck has used a different package. So this is just to point out the difference to before. All these leaf states here in gray are no longer compliant. That's why they are not available in the last layer of our compliant path graph. Any questions about this? Okay, we're now ready to define the decoupled state space. Another quite lengthy description of how we have to pay attention to the compliant path graph, and in combination with the center action to actually be able to exactly capture the state space. So to be able to have a complete and optimal search algorithm. So basically as before, we have SF, which is the set of all decoupled states. So all different center states together with all different pricing functions. We have the initial decoupled state, which is the initial center state. So we project on only the center variables, and then our initial decoupled state is just the center state projected on the initial the center variables projected on the initial state. Obviously, our center path is empty. We have not done anything yet, and the pricing function captures the cost of all cheapest compliant paths that lead from the initial state of each of the leaves to this state in the compliant path graph. So basically this is like in our example here, this first transition, we can choose to load the package into the truck and thereby like extend the original initial state. And then we have the set of all decoupled goal states, where again we need the center state to fulfill all our goal conditions, which is this statement here. And additionally, for all leaf states, for all leaf factors, sorry, that have a goal condition, we need a leaf state SL who fulfills this condition, and it must have a finite price. Otherwise, if the price of such a state is infinity, it cannot be reached, and we cannot extract a plan from this decoupled state. So what's more interesting is the transitions in the decoupled state space. Now, in contrast to before, the transition labels are only the center actions. As I said, we only apply, in our example, the drive actions, only center actions. The cost function is restricted to the center actions. And we have a transition in the decoupled state space from a state SF to a state TF. Whenever appending AC, so the label of the transition, to the center path of the first state, we get the center path of the second. So we just append one action to the center path. Applying the action to the center state of the predecessor results in the center state of the successor. That's the third one. The second one is obviously the center precondition of the action needs to be fulfilled in the predecessor, otherwise we cannot apply the action. And now for every leaf factor, again, where if our center action has a precondition on this leaf factor, there needs to be a leaf state with finite price that fulfills this leaf precondition. In our example, like in the second example that I've shown you, if we choose package 1 to fulfill the precondition of the drive action, so we can only drive if package 1 is loaded, then we need a leaf state, namely a package in the truck with a finite price, so that we can apply this action. And obviously, other than that, after applying the center action and updating the prices, we add all possible new compliant paths within this layer. So that's basically if we've driven the truck from 1 to location 3, a new possibility is now to unload the package at location 3. So again, let's do a short example. This is again the initial state of our running example. Nothing changed, so we have the truck at location 1. We have package 1 that is either at its initial position for cost 0 or in the truck for cost of 1 load action. Same for package 2, and for packages 3 and 4 we could not do anything yet. Now say we apply the drive action, we drive from L1 to L2. This allows us to update the pricing function. So basically we do not get any cheaper paths for locations L1 and the truck. Obviously, I mean, we cannot get back to L1, or if we unload the package at L2 and load it again, this would be 3 leaf actions for the truck state. And the new thing that becomes available is we can choose to unload the package in the middle. And this is actually the same for package 2. So this is really 2 at the same time, because they're independent of each other. So say we drive on again from L2 to L3, then like before, this also makes this new leaf actions applicable, where we unload the packages from the truck to location L3. And for packages 3 and 4, we can now choose to load them into the truck, because the truck is now over here. We can just load them at a cost of 1. Again, our example where the truck is not allowed to drive empty, so it must have a package loaded. The initial state does not change as before. If we drive from L1 to L2, given that package 1 is loaded, now what the difference is that the location L1 for the package 1 has a price of infinity, because in this decoupled state here, we can no longer choose the package to be at L1. The only option that we have is to keep it in the truck at a cost of 1, because we loaded it in the initial state, or we could unload it at location 2, which is price of 2, because loading in the initial state and unloading in L2. Say we drive on again from L2 to L3. Now we choose to have package 2 in the truck. Then basically for package 1, the options of having it in the truck and in L2 remain. because there was no precondition, no leaf precondition on package 1. And again, we have the additional option of unloading it at L3. And now for package 2, basically the options of having it in L1 and L2 are not there anymore because we have to have the package in the truck. So this precondition here forces us to have the package loaded, and the only options that are left is keeping it in the truck or unloading it at L3. Okay, so after many examples and lengthy definitions, here's some more definition that's not so lengthy, namely hypercubes, which are really quite intuitive way of understanding decoupled search, decoupled states. So we call an explicit state, so a full assignment to all variables, a member state of a decoupled state, if the assignment to the center variables equals the center state of SF. And for all leaf states, we have, for all leaf factors, we have a leaf state whose price is finite, so a reached leaf state, such that the assignment to the leaf variables is exactly that of our state P. Furthermore, we say that such a member state P has cost SF of P in this decoupled state, where the cost is just the sum of all prices of the leaf states out of which P is composed. So basically P consists of the center state of SF plus all possible combinations of reached leaf states, so of leaf states with finite price in the pricing function. And we call the hypercube of SF the set of all member states of SF. And we denote this by this bracket. So one example. Basically, this is like the notation as before. We have different prices for all the leaves, and we have a single assignment to the center. And now the hypercube of this decoupled state actually contains 24 member states. And it's all combinations where, so these are all explicit states. It's all combinations of states that have the same center, plus all possible leaf state combinations. So basically what we can choose from package 1 is these 3 leaf states. We can, this is like multiplied with all choices that we have for package 2, multiplied with all choices for package 3, and the same for package 4, which results in 24 possible states. And each of them has also a price assigned to it, which is then just the sum of all the leaf states that we have chosen. So say we choose for package 1 it to be in the truck, package 2 the same, package 3 we leave it at location L3, and for the same for package 4, then we have a member state of this decoupled state with a total cost of 2. This means that in addition to the center actions that we have applied to reach this decoupled state, we need to apply 2 leaf actions to get to this member state. So why are these things called hypercubes? Well, basically you could imagine a hypercube whose dimensions are the leaf factors. So every leaf factor is basically one dimension. And if we have like 4 packages, that will be a 4-dimensional hypercube. And the points in this cube are basically all possible combinations of these of the leaf states that you have. So basically, every axis contains or has discrete possible values, and each of these values is one assignment to your leaf. And this is really, I think, a nice intuition to understand where this exponential reduction from decoupled search comes from. So given that the packages are conditionally independent, we are able to just enumerate all possible paths, or I mean here in the compact representation of the pricing function, and this really represents a huge or exponentially large set of explicit states. To say a bit more about hypercubes, basically the hypercube of a decoupled state SF contains all states that are reachable on a path pi whose subsequence is exactly the center path of SF. So given a sequence of drive actions, the hypercube, or the set of all member states of the decoupled state at the end, is identical to all explicit states that can be reached on any path that contains this center action subsequence. And then it's like extended by any combination of leaf states, of leaf actions. Yeah, so basically, oh yeah, I should have shown that. Yeah, given this sequence of center actions, basically all possible or compliant leaf paths that can be embedded into this center action sequence lead to one of the member states of the decoupled state. To conclude this section, I want to show you two examples, basically one where decoupled search works really well and one where it doesn't. So this is like a slight modification of our running example where you have a sequence of locations and the truck can drive between any connected locations, and you have n packages. And now the point is that in the initial state, the decoupled search can choose to load or keep at the initial position all possible combinations of these n packages. So what you have is a single decoupled state that encodes all these possible combinations, where in explicit search you have 2 to the n reachable standard states just to load different numbers of packages. The overall size of the state space of this example is 15 for decoupled search, and it's 5 times 6 to the n for explicit search. So as you see, the decoupled state space size does not even depend on the number of packages. It is just all compressed into one decoupled state. Now an example where it really doesn't work. You see it doesn't really change a lot. The only thing that changed is like that there are some it's like branches in your roadmap, and basically once you have that, if you drive from A to D via the two different paths, the resulting explicit state will be the same. For explicit search, it doesn't matter how you reached location D. For decoupled search, it does matter. And this is because, say, one drive action sequence goes from A via B to D, then the pricing function of the leaf state of having the package at B is 1. Is 2, load, unload, and the same for D, but the price of having the package at C is infinity because you cannot unload it there. Now, the second path, if you drive from A to C via D, it's just the other way around. So you can have the package at C, but you cannot have it at D. And so this results in two different decoupled states once you have reached D, and you cannot say that one is better than the other. You need to keep both of them. So you could say that the decoupled state remembers the center path that you have taken, and in this case the decoupled state space is actually exponentially larger than the standard state space.
Why can't we just join the two decoupled spaces?
Well, because they arise from two different center paths. So if, say, you choose the center path up here, you cannot simply choose to have the package at C, right? So it's the enumeration of all possibilities for the leaves is always only given the center action sequence that you have executed.
Okay, you would have to make an approximation saying I could also get here via C, something like this.
Yeah, you would have to do something like this, but this is then like combining two different center paths, and again then you get some explosion in the decoupled state where you need to keep track of all possible ways how to reach a state. Yeah, I mean it's a nice idea to think about. Not sure, maybe you can get something out of it. I'm not sure yet. I will keep it in mind. Thanks. Now, in our example here, we only have a single package. If you have both effects, like such as strange, like a pretty common roadmap and multiple packages, then both effects occur, right? So you have the exponential reduction from being able to compress the multiple package movements into the decoupled state, and you have to blow up because you remember the path that you've taken, and then it's really hard to tell if it's going to work or not. Really, it's a trade-off between the length of the map and also the number of packages that you have. Okay, so with this, I'm basically done for the first part, and Álvaro will tell you how to use heuristics and dominance.
Well, now we want to use heuristics in the decoupled search. So, well, as before, heuristics are a function that assigns a numeric value to its state in the planning task, and this numeric value basically is estimating the goal distance of this state, right? In the examples that Daniel has been showing in the slides, we are always showing one single center path. But of course, in decoupled search, what we have is that we start from an initial decoupled state, and then we might have more than one possible center actions applicable in this decoupled state, and then we reach different decoupled states. And the question is, can we use heuristics to estimate the distance from this decoupled state, or from every decoupled state to the goal? And the point here is that, of course, what we have here is not a single state, but we have, well, basically, as usual, we have the center state, which in our example is the position of the track, plus a pricing function that tells us for every package what's the corresponding price. Okay? So the question is, can we use this kind of heuristics that estimate the distance from one state in order to estimate the distance from a decoupled state, which is really a set of states, right? So first of all, we need to decide what we are trying to estimate there. And we have basically two choices. So basically, we are going to call decoupled heuristics to anything that maps a decoupled state to a value. But what's this value really trying to estimate? And we have basically two different choices. We can estimate the center distance, or we can estimate the star distance, basically. So the point is, in this search, all these actions that you are applying in the search, all that you are branching over, is always center actions. Leaf actions are encoded, implicitly encoded in the pricing function, but in the search, you are only branching over center actions. So if you are trying to estimate the distance to the goal, it might make sense to have an heuristic that only depends on the cost of center actions. And this is actually useful because basically this measures what's actually the distance in your search to a goal decoupled state. In practice, we use this kind of heuristics if we want to do satisficing search, because we don't care about the cost of leaf actions. We only care about reaching the goal in the least number of center actions as possible, because we want to reach it as soon as possible. Now, if you are trying to use optimal planning to compute optimal planning, what you want to obtain is an as good as possible lower bound for the total cost of reaching the goal, and therefore you need to take into account basically not only the cost of the center actions, but what will be the cost of or the price of the leaf goals at the end. And well, basically we say that an heuristic is center admissible if it's an admissible estimation of the distance only taking into account the center actions, and it's star admissible if it's admissible taking into account also the price of the leaf states. Okay, and then we can define center heuristics and star heuristics. And then now we know what we want to compute. And now the question is, how can we use standard heuristics in planning to actually compute these estimations, right? So this is possible just by doing a compilation. So we can use any heuristics defined for classical planning, which is defined for the states, and we are going to just slightly modify our planning task in order to use this heuristic. And the way that we are going to modify the planning task is the following. So in this state, we know that the track is at L2, and the packet can be either at the initial location L1, or at the track, or at L2 by a price of 2. And the rest of locations have a price of infinity, right? So how can we modify our planning task in order to use standard heuristics to get an estimation from this? All that we need to do is to add auxiliary actions that achieve all these facts. So basically we will add actions that have no preconditions and that as an effect has its leaf states that it's reachable in this current state with a finite price. The intuition behind this is that, well, we have already achieved all these states via the center path that we have taken, so we can allow the heuristic to achieve it for free. And if we are in the center heuristic, basically all these auxiliary actions that achieve this leaf states will cost 0. And in the star heuristics, basically, it's all these auxiliary actions will have the price of the leaf state. So basically, we have an action that adds the fact packet 1 at location 1 with cost of 0, another action that adds packets 1 at location cost with cost of 2, and so on and so forth. Yeah, and basically that's the basic idea. Note here that for every different decoupled state, we have different auxiliary actions because, well, basically we have one auxiliary action for every possible leaf state that is reached or that can be reached with a finite price. So basically this is going to be different for each decoupled state. But in general, this is no trouble. You can just compute this, add these actions to your planning task, compute the heuristic in that different planning task, and use the estimation for your search. And if the heuristic is admissible, basically star admissible was what we want, but of course central admissible would be okay too. We can guarantee optimality. But to do so, we have to somehow make a further modification. So suppose that you apply one center action and another center action here, and you achieve one decoupled state, SF2, and this decoupled state is a goal decoupled state. The question is, you have found a solution, of course, for your planning task, but the question is whether this solution is guaranteed to be optimal. And it's not if you just stop the search at this point, because, well, basically this is achieving all the, or one leaf, goal leaf state for every leaf, but the global cost is not guaranteed to be optimal. So what we need to do in order to guarantee that this is optimal is to add an artificial final goal state. Let's call it SG. This is an artificial state. And then from every goal state, we add an action to the artificial goal. And the cost of this action, this is the key part, will be equal to what's the goal price of this. So basically, imagine this example here. We have this state that achieves our goal. In this case, our goal was to have package 1 at location 3, package 2 at location 1, and package 4 at location and package 4 in the track. So what's the cost of this auxiliary action here will be 3, because we can buy all these fats by a total cost of 3. And that's the intuition. And if we just do this modification and apply A star search on this graph, then, well, A star will know when the solution is optimal as usual. So basically, the A star search is aware of the cost of all these center actions, and all that we need is to add the cost of all the leaf actions just at the end in order for A star to be able to prove optimality. So basically, here in our example, we will have a transition here with cost 3, and that's it. Yes?
Does it mean the task changes for every heuristic you evaluate? So, for example, if you have heuristics that do some precomputation based on the goal, would you have to redo the precomputation for every heuristic?
No. So this is not an heuristic. This is just changing like my applicable graph. So instead of considering that a goal decoupled state is a goal in the search, because then A star will say, okay, you have found a cost you have found a path of cost 2 to the goal, right? This is a goal. A star will say, okay, I have found the goal with cost 2, but this is not cost 2. This is really cost 5 because you still need to apply the leaf action somewhere. So the way that you modify this is that so the only applicable action in this state, being a goal state, is buying all the leaves. Oh no, sorry. Actually, you can apply other center actions here, because actually the optimal path could be this one, right? So it might be possible that after applying 4 center actions, you can buy all the leaf states by a cost of 0. So basically, that's precisely the point. You add this auxiliary action that allows you to achieve the goal immediately, or maybe you can also achieve the goal via some other cheaper path. And just applying A star on this modified graph will work out of the box.
But could you use that for heuristic calculation? Could you use the cost, add this to the heuristic value or something?
Okay, now I get you. Well, somehow you are doing that when we are saying that for the heuristics we compile, we do this compilation that allows you to buy all these states by their price. So in some sort you are already doing that.
Just as a remark, what you could do is maximizing over the heuristic value that you computed and the minimum summed up cost for each of the leaves. So it might be that the heuristic misses something or does not capture all the leaf prices, and then you could always maximize over heuristic value plus what you know is the minimum cost for each of the leaves.
Mm-hmm. Okay, by doing this reformulation of adding this artificial goal and these artificial actions, any search algorithm that it's optimal in the standard state space search will be also optimal if you apply on this graph. So the only thing that we are modifying here is basically the semantics of each node and what it represents, and also this artificial goal. But any algorithm will work out of the box. Yeah, and just another remark. Daniel was saying before that these hypercubes are good to understand intuitively what's happening. So remember that each of these decoupled states is just a set of states again. Of a very particular form, in this case an hypercube, associated with one cost. So whenever we compute an heuristic for a decoupled state, what we are really doing is to estimate the minimum heuristic value of all these possible states. So basically you are choosing one of these states, or well, not choosing, but you have to compute the value of all of them and then take the minimum. And that's really the admissible estimation, because basically the idea is that these decoupled states represent a lot of possible states. You could be in any of them, the one that you want, and that means that you have to minimize over all of them to compute the heuristic value. And intuitively, this is captured by your approach, because by adding these actions that allow you to buy these leaf fats by their price, you are basically allowing the heuristic to transition to any of these states by their current price. Okay, so that's a about how to apply heuristic search, but there is still a problem if we apply a standard A-star search in this graph. It won't work at all. And the reason is that duplicate checking is just not good enough in the coupled search. So the point here is that if you have a decoupled search, what's the likelihood that you are going to find exactly the same decoupled state? And that's very low. Maybe I can find a very similar decoupled state with very similar prices, but not exactly the same. So we don't want to do duplicate checking because of that reason. It won't be good enough. And what we can do instead is to use dominance relation between over the coupled states that prune an state if it's strictly worse or worse than another. So the question is, what does it mean, better or worse? And a very, very easy criteria that we can use is if you have a new generated state and you have previously seen one state such that for every possible price that you have in your pricing function, the value of this state is lower or equal than the value of this state, then this state is better than this one. And of course, I'm only talking about states with the same center state. So basically, if you have another state with the same center, and for every possible leaf state has an equal or lower price, then the state on the right is just better, right? So basically, you can prune the new generated state in this case. You don't do a SAT duplicate checking. These states are not equal, but you do this dominance checking. And it's a very simple criterion of dominance, but it works very well in practice. Now, you might be wondering, could we do better than this? And well, the answer is yes. So what you could try to do is the following. Given that you have a new state, understanding this new decoupled state as an hypercube, so a set of states, the question is, have I already seen all the states that are in this set? So if I have a bunch of decoupled states that I have seen earlier, of course with the same center, because, well, for the center being just an assignment to the variables, you can do duplicate checking just in a standard search. So given all those hypercubes, the question is whether I can prune the new state. And the answer is, well, yes, you can prune it if basically all the states in the hypercube, of the new decoupled state, so all the states of the new decoupled state are already contained in the union of all the sets of states that you have visited so far. So basically, if you consider each of these decoupled states as a set of states, this is quite intuitive. If you have already seen all the states in the new state, then this state is a duplicate, right? But of course, this is not so easy to do because, well, computing the union of all the previously seen decoupled states is not going to be easy. And actually, well, this would be great if you could do it. It would give you a size guarantee. So basically, this, if you could do this, it could guarantee you that you are never worse than explicit search. As Daniel told you before, he showed you an example where decoupled search is exponentially worse than explicit search. And if you could do this, then you could avoid those examples completely. But this is an NP-hard problem. And basically, doing this check in this way seems completely infeasible, and you can actually do better. There are some algorithms like curve elimination by Hoffman and Coppersmith in 2005 that allow you to do this, but, well, being NP-hard, of course, you cannot do this in polynomial time. And this is what I'm talking about here is only for for satisfying planning, of course, because I'm talking about sets of states without their price. If you want to guarantee optimality, you will even need to have into account the prices. So we are not going to enter into this here. We have also worked on some other more advanced dominance criteria for decoupled states, but well, it's not the purpose of this tutorial to go into that. So now I will return to Daniel, that is going to explain you how to actually automatically find the structure that you want to exploit in every planning instance.
Okay, so just as a follow-up on this, it's related to your question. Basically, with hypercube pruning, you would see that, like not in the first step, but in the second. So if you have this branching on your map, you drive to the second location, then you have two different pricing functions, right? So if you then drive further on to the next meeting point of your map, you could then see that the first two decoupled states actually together, so if you take the union of that, then this is together is more than one of the successors. So and at this point you could prune one of the states. And this is actually where in the bad case example we can now guarantee that the size of the decoupled state space is upper bounded by the size of the explicit state space. Again, for efficiency reasons, we obviously don't do that. So as Álvaro said, I'm now trying to explain how to actually find good decomposition methods, like how to factor our planning task. To do this, I will briefly recap what a causal graph is. I guess you're all familiar with that. So basically, a causal graph captures the dependencies between state variables, and the nodes in these graphs are the variables, and we have a connection from one variable to the other if there is an action where one is in a precondition and the other is in the effect, or if there's an action where both are in the effect. Now, an important notion for decoupled search is what we call the interaction graph, which is like a quotient of the causal graph over our factoring. So here in the interaction graph, the nodes are the factors, and we have a transition in the interaction graph from one factor to the other. If in the causal graph there exists a variable in one and another in the second factor, such that there is a transition between those variables, and they are in these two factors. So it's really, you take the causal graph, you put the factoring on top, and this is your interaction graph. As promised in the introduction, I will now point out the differences to prior work on factored planning, where in general factoring is a partitioning of the state variables just in decoupled search, and there's been really lots of prior work on factored planning. Many people have worked on this. The biggest difference to what we do in decoupled search is really that they did not require any kind of dependency structure between their factors. So intuitively, this was really motivated by multi-agent planning, where you just have the agents that interact with each other in whatever possible way. So direct interaction between agents, cross interaction across multiple agents, and so on. And really the weakness of many of these approaches was that after solving the subproblems, it's somehow they had to combine this again to get a global solution, and this was really for most of this work, this was a tough problem. Some of the more recent works used CSP encodings to handle this. In general, I think none of the prior work was really able to do optimal planning. So the most they could get was local optimal plans, so within each subproblem, but there was no global optimality guarantee. Now, what we do in decoupled search, we have to have this star topology. If we don't have it, decoupled search does not work. So this is really a strict requirement that the interaction graph has one center component. In our running example, that's the truck, and there are leaf components around, and the only interaction is between truck and packages. Now this is like the definition of a star factoring again from the introduction, and this is one possible factoring. Now, not our running example, but an arbitrary one, and each of these factors can contain many variables. Now, I kind of lied to you in the beginning, because actually this definition allows for interactions like this, like the ones marked in red. Just because there might be center actions that affect multiple leaves at the same time. And if you have this, say you have a center action that has an effect on FC and on leaf 1 and leaf 2, then this induces a causal graph connection and thereby an interaction graph connection between these two leaf factors. And this is all good. We can really handle this in decoupled search. The question is just, will it give us anything? So really the important point in decoupled search is the conditional independence, and by having such actions we introduce actually some dependencies between the leaves. So the question is, how much can it give us? And that's why in all our work so far we really focused on strict star factorings, where these red dependencies here do not occur. So we can have arbitrary interaction between one leaf and the center, but no interaction across leaves. So strict star factoring is a factoring where the transitions in the interaction graph are either from the center to a leaf, from a leaf to the center, or these bidirectional things. That's it. Oops. So how to automatically find the factoring? Well, there are easy cases and there are hard cases. In most of our prior work, we focused on the easy cases, where by analyzing the strongly connected components of the causal graph, you could easily identify a factoring. Fork structures and inverted fork structures are really well known in planning. There are many works that try to identify such structures and thereby exploit certain properties. And this is also what we captured so far or mostly in decoupled search. It's as easy as just taking the causal graph leaf for fork factorings or root components. You can just easily read that off your causal graph, and that's it. Your factoring is done. You take the leaf components as leaves, you take all the rest as the center, or the other way around for inverted forks, and you're done. We also devised a easy combination of this, which we call X-shaped factoring. So we do a fork factoring, and then you can do an inverted fork on the remaining center part, so that, well, you could imagine having edges from the package to the truck here, and also from the truck to the packages. What you need to take care of are leaf-leaf dependencies. So it might be that there exists an action that induces an arc from this package to this one here, and then you need or you might have to put variables back into the center. There are some really important criteria about factorings. So the most important thing is really the number of leaves, because as you have seen before, the potential gain over explicit search is exponential in the number of leaves. That's why we really want to have as many leaves as possible. But there's some other really important criteria as well, namely the leaf flexibility. The leaf flexibility basically captures how much work a leaf can do on its own. So basically, with our packages, you have really maximal flexibility, because all actions that affect the packages, so load and unload, are leaf actions. They do not affect the center. Now, say in our, or say you had a center action that loads all packages at the same time as driving to a different position, then this center action would also affect the packages, right? Because it would load all packages and drive. It would affect the packages, but the search has to branch over this action. So it does not give us anything to reduce the size of the search space. In the extreme case, what we call frozen leaves is all variables that affect the leaf also affect the center. So we need to branch over all actions that affect the leaf, and in this case, this leaf is just useless, and we can push it back to the center, removing this leaf factor. There are other criteria, like the size of the leaf. Like we estimate this by the domain size product of all variables contained in the leaf. This is really relevant for practical reasons, because it incurs a big runtime and memory overhead if you have really a huge leaf state space. In case of the packages, that's obviously negligible. They don't have so many possible states or positions. But if you have components of leaves, components of variables in a leaf, that can get really a big overhead. Another thing is the structure of the leaf state space. So think of a leaf state space that is strongly connected, like the one for the packages. You can reach every possible position from every other position. There are special cases like that might be exploited. We don't do that so far, but I guess you could be able to do something about this. Now, an interesting result theoretically is that to get the maximum number of leaves in a strict star factoring, the maximum number of leaves is equal to the size of a maximum independent set on the causal graph. This is because, well, if you choose, if you compute your maximum independent set on the causal graph, put every variable that is in the set in a separate leaf, then you are guaranteed to have no causal graph connection and thereby no dependency between your leaves. So this is really the best you can do. Unfortunately, as you see here, where we have marked the variables in the maximum independent set in red, this is not really the idea of decoupling. Like the decomposition is really bad because your center, which is then would be the black variables, is not even connected. And structure like this here, where you have three variables that are very closely connected, you would really ideally want to have those in a single leaf and not distributed across leaf and center. And here's also what's important, the leaf flexibility. If you have such a case, it's very likely that the flexibility is very low, so that many leaf actions also affect the center, and therefore you need to branch over them. So we have devised this maximum independent set strategy, which, if you're interested in that, there will be a talk tomorrow in the HSDIP workshop where I'm going to explain this in more detail. So basically, given a maximum independent set, we apply some post-processing to really capture this structure of the problem, or we try to do that. And if we have less than two leaves, well, we just stop and run standard search instead. Otherwise, we use this factoring and do decoupled search. On some instances, though, it's really infeasible to compute a maximum independent set. In the implementation, we fixed this by setting runtime limits. So we we look for the independent set for a while, and if we don't finish, we just pick whatever we have found until this time. Another approach is a very greedy strategy that sorts the variables according to the incident arcs, so the number of connections in the causal graph, and it puts the most densely connected causal connected variables into the center. So in our example here, it would start by putting the variables with three causal graph connections into the center, keep iterating until everything is in the center, and then just choose the factoring that has the maximum number of leaves. Basically, so we say we put these two variables here in the center, then this would nicely decompose our task because we would have one leaf here, one leaf there, and one here. All of them are weakly connected, so this really is like ideal in the sense of it really captures the dependencies of the problem. Another really important thing is the factoring time. So here are some results for our different factoring strategies. As you see, the very easy ones really finish in split seconds. The runtime is always below 0.1 second. For the independent set factoring, it actually can take a while, even though we have like this timeout. It can get up to 30 seconds. But only very rarely. I mean, observe that here's already 70% of all instances, and in 75% it really finishes in split seconds. Then there are some where it takes a bit longer, like up to 1 second and so on. For the incident arcs, like the greedy methods, everything finishes within 10 seconds at most. Actually, mostly below 5 seconds. We would now go into the implementation. Is there anyone actually willing to participate? Or you just want this to be over and go home and have dinner?
What does participating mean?
Well, participating means like writing around 10 lines of code. But if you're really not motivated, I can also do it basically myself and explain while I'm doing that. Everyone prefers that?
No. Wouldn't mind participating.
Yeah? Okay, well, in this case, we do a very brief break. Actually, we're not going too well on time. Yeah? We can do that? Okay, so...
This is going to go till 5:40, so I would say try to cut it off at 5:40.
Okay. I guess we can manage that. Yeah, so basically a very short break for all those that want to participate. Here's some instructions. You need to clone a repository and update to the branch that I provided. The relevant files are listed, yeah, and so on. Basically, this is already working quite well. I mean, it will reduce the number of evaluated states by a factor of 2, if I remember correctly, compared to blind search. So everyone who's willing has copied the URL and also the branch. Then I would just proceed and explain a bit about fast downward and decoupled search. Okay. Okay, so this is really a major simplification, and probably Malte will beat me for that. Say this is fast downward. So we have the search algorithms that are like the most important part. They interact with the state representation, which is called the state registry, which keeps track of all states. We have the successor generator that tells the search, given a state, which actions are applicable. We have heuristics that are used to guide the search, and we also have or can have pruning techniques like partial order reduction, symmetry pruning, dominance pruning, that further reduce the size of the search. Sorry, the size of the search space. So the interesting thing is that everything that's marked red had to be adapted to run decoupled search. The search algorithms really not. This is modulo, the adaptation that Álvaro was mentioning before with this artificial goal state. Obviously, we need to add this transition to be able to guarantee optimality. Other than that, obviously the state representation is completely different, and then it's only the endpoints really that need to know about how a decoupled state looks like the heuristics of course, like Álvaro explained, pruning techniques as well. We will mention some papers later, and the successor generator obviously needs to know that it only outputs center actions, and furthermore it needs to check the leaf preconditions in the pricing function. So how do we represent decoupled states in fast downward? Basically, we have a decoupled state registry, which in fact is many state registries. We have one registry for the center states that stores all different center states, and we have one registry for each of the leaf states, so that we really only store each leaf state once. Then every decoupled state is a pair of a center state and an instance of what we call the compliant path graph. That are the objects that basically keep track of the pricing function. Like as a really nasty hack, we had to add an auxiliary variable to the center states to keep track of multiple decoupled states with the same center state. So this is really to distinguish the decoupled states that have the same center. We introduce a new variable that is initially 0, and we just keep incrementing it for every new decoupled state that we see that has this center. The search algorithms, as I said, really use only these augmented center states. They don't care about the internal representation of decoupled states, actually. And accessing the pricing function works by what the insiders might know as this per state information thing, which is like a huge vector that has an entry for every augmented center state. and looking up the value for like this compliant path graph objects in this huge vector, then gives you for each of the augmented center states the pricing function. Compliant path graphs, well, there are really many of them. We have specialized compliant path graphs for optimal planning, where we really store the prices. For satisficing planning, where we only store true false if a leaf state is reachable or not, where we don't care about the cost. We have more elaborate compliant path graphs for dominance pruning, like for more complex than the one that Álvaro explained to you. And actually, the ones that have been at SOX a few days ago also know that we have symbolic leaf representation, where instead of really keeping this pricing function explicitly as a kind of table, we have a BDD that represents all the prices. As I said, in the pricing function in optimal planning is basically a vector of ints for each leaf vector, which is indexed by the leaf state ID. Nothing special about this. Updating the pricing function then is running a uniform cost search from the set of all reached leaf states that we have in the current decoupled state. We run until a fixed point is reached, so until no more prices decrease, and we have our new pricing function. This is done after every application of a center action. As I said, we cache the entire leaf state space just for efficiency, because we really need to apply these actions so often. Otherwise, this would take ages. So then here's like the important part also for the hands-on, which you will need later. I have it on another slide. This compliant path graph storage basically is what I told you, this per state information thing. So this really large vector that for every decoupled state keeps a pricing function object. You can access this globally so that it can really be used in heuristics, pruning, in the successor generator, wherever you need it. And these are the functions that with which you can query information from the compliant path graph. So as I said, the indexing is really via leaf state IDs plus the ID of the leaf vector of this leaf state. You can ask if a leaf state is reachable in a compliant path graph. You can get the cost of this state. You can query how many leaf states there are in the compliant path graph, and also if the goal is reachable. So if there exists a leaf state with finite price that is reachable. That is goal leaf state. Sorry. So this is really now the part where it's you that need to work, and just as a warning, it's a mess. This is like a one-man project, and whenever Álvaro is helping me, it's getting even worse. So I would be happy if I found some collaborators, because it's really a huge change to the entire fast download system. And as Álvaro already said, for the symbolic search, it's impossible to keep track of all the updates that the guys in Basel are doing. I mean, I would have to work only on this the entire year to really be always up to date and have a nice state representation. Nevertheless, you're obviously encouraged to take a look at the code and also use it. I mean, usage is not as bad as implementing new things. So basically, here's what you will, or part of what you will need to implement your heuristic function. So everyone who's willing to participate has opened this ICAPS heuristic file. Oh, I don't have it anymore. So as I said, we will implement a mixture between goal counting heuristic and PDB heuristic. And to do this, some more explanation. So basically, this global minimum cost is a vector of integers that for each of the leaves, so it's indexed by 0 to number leaves minus 1, has pre-computed the minimum cost of each leaf to reach its goal position. That's one of the things that you need, and then you can basically use it as a PDB where you need to check for the maximum cost. So let me just open the editor. Can you read this? Okay, roughly. So basically what you want to do is you have the result for which is the difference between the current minimum price of a leaf state and the minimum pre-computed goal cost of this leaf. So you would have to iterate over all leaves, which you can do by a for loop that roughly looks like this. So in the G factors, we basically store all leaves. So this is how you iterate just over all leaf factors. Now what you have to do on top of that is iterate over all leaf states that are reachable in this state, and that have like a finite price. So obviously you need to uncomment this line up here to get the compliant path graph object. And then one more trick that I need to show you is basically that how to iterate over all leaf states of a factor. And this is quite nasty still because it needs direct access to the state registry. So as usual, this is like also pretty nasty hack. All leaf states start with ID 0, and then you increment the ID until you reach the number of states. And you can query the state registry for the size, so the number of leaf states, by asking for the size of a factor, of a leaf factor. Yeah, so I guess this is like the most important thing. And now what you need to do is basically iterate over all, query the compliant path graph object for the cost of all leaf states that have been reached, and add this gmin cost value minus the minimum price to the result, basically. Oh, well, I should probably open. So this is like the functions that you can use to query the compliant path graph. So one thing you need to pay attention to is that getting the cost of a state that is not reached is kind of undefined. So that will probably result in an error. So you first have to check if a leaf state is reached. We're running short on time, so I could just help a bit. So this is how you check if a leaf state is reached, so if it has a finite price. And then what you would have to do is keep track of the minimum price. Obviously of the maximum price, sorry. So something like this. For each of the factors, you get the leaf state with the maximum cost. Well, obviously I'm missing the max. and then basically minimizing the difference. No, it's minimizing the difference. So basically what you do here is really very close to a PDB. Since you are dealing with a set of states and not only a single state, you basically need to query for all member states. Well, not really, you do that only projected on one leaf. What's the minimum cost from a leaf state to reach the goal? So basically you need to take the minimum goal cost and subtract from that the cost of a state, and if you minimize this, then this will give you the minimum estimate for this leaf factor to reach its goal. No?
Missing a negation in the if?
Yeah.
Unless it has to be initialized to a high value.
That's probably also true. Something else missing or broken?
You need to ensure that the minus is not lower than 0, right? Max of 0.
Any more mistakes?
The rest values never changed.
Oh, yeah, of course. Any more suggestions? So let's just try. Let's build. So what I've run before is basically a blind search on an instance of no mystery, where plan length is on cost is 23. We have evaluated 9,600 states, and now let's see if our heuristic is any better. And it's actually not. That's a bit bad. It's the same instance. What am I missing? So at least you see something, namely that the initial state value is 14 and not 1 anymore, which basically means that we have 7 packages. So for each of the packages, we need to apply 2 actions: load in the initial state and unload at the goal position. Not sure why we have this blow up here. Let me think about it. Any ideas? Probably just some mistake in the implementation.
If you have not reached the goal, you have to add 1.
Well, anyway, so basically what I want to tell you with this, it's really easy to implement easy heuristics in decoupled search, although as usual there are always bugs in your implementation. Really, I want to encourage you to try to work on decoupled search. Implementing or thinking of new heuristics is, I think, not too complicated, given that all the really crucial stuff like how to run the search, dominance pruning, and all this is set up. Implementing a heuristic for this should be fairly easy. So let's go into the open topics. That's just what I said. The basic framework is established. We have really an implementation at hand that's working pretty well, although there are some hacks in there. We have also lots of extensions implemented, like the factoring methods. As I said, I will talk to you about this in more detail at HSDIP tomorrow. We have partial order reduction that is working. Symmetry breaking, again, that's going to be a talk on Friday morning at ICAPS. We have done some more complicated dominance criteria. And we have also combined it with symbolic search to compactly represent the pricing function. There are obviously many other things you could do, namely different formalisms of planning. So think of numerical planning, where you could easily enumerate intervals of the numeric variables in the leaves, which is quite natural to do and should be fairly easy to extend the decoupled search framework to numeric planning. Regarding probabilistic planning, we've already had a master thesis who was a guy who was working on that, who was basically building and/or trees in the leaves. giving a deterministic center, temporal planning, generalized planning, and many more. What I said before, really regarding the heuristics, we are currently quite limited. Those are all roughly from the delete relaxation family, Hmax, HFF, LMCut. It's certainly possible to connect to different types of heuristics, like abstraction heuristics, merge and shrink, Cartesian abstractions, or LP-based heuristics. Maybe it's possible to easily capture the structure of decoupled states in an LP. Landmark heuristics should be rather easy, I would guess. Or even beyond classical planning at all, like why should we really work a lot on how to identify the decomposition in our IPC benchmarks when we have multi-agent planning or multi-agent system, so where the multiple agents interact on a set of shared variables? This is really natural application for decoupled search. Same goes for model checking. Think of client-server architectures and also parallel processors that share a memory, like many CPUs working on the same memory. You need to have certain safety guarantees. Then there's the open question of decoupled search versus PetriNet unfolding. Can we prove any formal relation here? And last but not least, like the take-home message, explicit search is really cool. It's very general. You can do everything, and it works well in practice. You have all the search algorithms, powerful heuristics, successor pruning methods, but it also has its limitations. Namely, it will never be able to capture the conditional independence as decoupled search is doing that. And this exponential gain potentially over explicit search is really the big advantage of decoupled search. And there's just no way to capture this if you keep the explicit state representation. And last but not least, decoupled search is really easy to use. You've seen that on our webpage we have linked a repository with all the code inside, and using it is really easy. I mean, you can easily integrate it into all your portfolios, or if you need to tackle problems that really have a star topology, just try decoupled search and see if it works. That's it. Thank you.